In this video, we're going to start Chapter 2, the integers. Again, everything in this chapter is review from probably something you've seen in a previous course, likely discrete mathematics or foundations. And in this section, we're going to review mathematical induction and the well-ordering principle. So, if you recall, mathematical induction had two different forms. The first one, the first principle of mathematical induction, says that if you have a statement S of n about the integers, well, non-negative integers, or the natural numbers, and we suppose that it's true for some kind of starting value, so n sub 0, a lot of times this is 1, a lot of times this is 0. We could actually take this to be along the integers as well, as long as you don't take all the integers. You have to have a lower bound or a starting point. And if it's also true that for any integer k that's at least as big as that starting point, that the truth of s, the statement s of k, implies the truth of sk plus 1. Then if these two things hold, then it's true for all integers beyond that starting point. I like to think of this as dominoes. Like if you have a bunch of dominoes, well, here we're imagining an infinite amount of dominoes. And in order to be sure that all of the dominoes will knock over, well, you first have to knock over the first one, so to get the process started. So this is kind of like our n0 here. And so, of course, that one will knock over the next one, that one will knock over the next one. But we need to be sure. You can kind of think of this, that every domino will knock over the one in front of it. So, for example, like if you had a bunch of dominoes, but maybe two of them were too far apart, and when it knocked over, it didn't knock over the next one. So you need to be sure that for any domino, say the k domino, that if it gets knocked over, it knocked over the one in front of it, the k plus 1. So as long as we're sure of that this is true for any k, then we know that they'll all eventually get knocked over. And then the second principle of induction is what we a lot of times call strong induction, or this first one we call the weak induction. Is a similar setup. We have Sn, a statement on natural numbers, where it's true for some starting natural number, n sub 0. And now we get to use something stronger. Like here, we have to only use sk to sk plus 1. Here we're allowed to use everything before, or sk and before. So we can use n0, we can use the truth of n0, the truth of n0 plus 1, all the way up to the truth of sk, to imply that sk plus 1 is true. And then if that's true, then again, it's true for all integers. And finally, the well-ordering principle, which we'll see is equivalent to mathematical induction, is that, again, this one probably feels like the most obvious of these statements, is if you have a non-empty set of natural numbers, is what we call well-ordered, which means it contains the smallest element. It contains a number that's smaller than every other element in the set. That one seems like the most obvious statement to make, but we will see that it's actually equivalent to our strong and weak inductions, and actually weak and strong induction are equivalent to each other. So these are all equivalent statements. Our first example here, one that you may have seen before, it's a common one to use for induction. The sum of the first n squares has this formula n times n plus 1 times 2n plus 1 divided by 6. So we'd like to prove this using, we'll use the first principle of induction, or weak induction. So the first thing to do is show that it's true for the base case. I'll put that up here. So what's the smallest value of n where this is true? Well, just the smallest natural number. We could actually start this at 0. Well, it kind of doesn't make sense on this side to have this at 0 because it's supposed to be 1, 2, up to something that's at least as big as 1. So it makes sense that our base case should be 1 here. But you could make the base case 0 and just say that an empty sum is 0, and then this side is obviously also 0. But let's try it for 1. So in the case of 1, you just have 1 squared on the left-hand side. And then we just plug in 1 for n on the right-hand side. So 1 times 2, 2 times 1 plus 1 is 3, all over 6. And that works out. That's 6 over 6, which is also 1. So that's the first step of an induction argument. Just check that it works on the base case. Now, the main part of induction is to show that it works, or that if it's true for any particular case, we'll call that k, that it implies that it works for the next case, k plus 1. So at the beginning of the induction step of a proof, we assume that it's true for some value k. So we just replace everything with k here. So 1 squared plus 2 squared up to k squared. And we'll leave some space here, is equal to k plus 1, 2k plus 1, all over 6. So we assume that's true, so it's our starting point for our proof. Now we'd like to prove that it's also true for k plus 1. So if I insert k plus 1 for all the n's here, that equation is also true, or it comes from this equation. So we want to sort of start here and work our way to the version of this where all the n's are k plus 1s. So one way to get that, at least for the left-hand side, is to add k plus 1 squared, because that's the next square that we would add. So we add that to both sides of the equation, just normal algebra rules. And now we have the version of this equation where n is k plus 1 on the left-hand side. Now we just need this. We can actually see what that would look like. If I let n be k plus 1, I have k plus 1 plus 1, so k plus 2. And then if I put a k plus 1 here, I get 2k plus 2 plus 1, so 2k plus 3, and still all over 6. So that's my goal for this right-hand side. I need to show that this right-hand side simplifies to this. So that's where the main part of the work that we'll be doing here is to show that I can simplify this to this, which is just some algebra. I need to get a common denominator. So I'll multiply top and bottom by 6. And so now I can write it all under 1, common denominator of 6. And notice there is already a common factor here. I could factor out a k plus 1. So I have a k plus 1. And let's see what's left over. I have k times 2k plus 1. I'll multiply that out. So 2k squared plus k. And here I'm factoring out a k plus 1, so I still have a k plus 1 left over, multiplied by the 6. So I'll multiply that through, so 6k plus 6. So I'll finally put these two together as a 7k. So k plus 1, 2k squared plus 7k plus 6, all over 6. And again, I'll put this as our goal up here. This is what we're trying to eventually get to. You can see we're almost there. We have a k plus 1 there. The 6 on the bottom is already there. All we really need to show is that this factors into this. And it's just, verifying. So it does indeed factor to k plus 2 times 2k plus 3. And you can just check that by multiplying it out. You get 2k squared. You get a 4k and a 3k, which makes the 7k. And you get 2 times 3, which is the 6. So that checks out. Showing those two things, I'll put this as the induction step. So showing the base case and the induction step is enough to show that the formula is true for all n, or at least for all n beyond the starting point. The next example, we want to show that 10 to the n plus 1 plus 10 to the n plus 1 is always divisible by 3. Now, if you think about what that would look like for any particular n, that would be two ones followed by some number of zeros, and then a final 1. So that's what that number would look like in general. And you may remember a rule for divisibility by 3 if all the digits add up to a multiple of 3, which this clearly does. So we know that that's true, that it's divisible by 3. But let's see how we could show that through induction. So again, base case would again be n equals 1. And when n equals 1, we get 10 to the 1 plus 1, so 10 squared plus 10 to the 1, and then plus 1, which is 111. But you can factor that quickly as 3 times 37. So that is a multiple of 3. Now, we assume that it's true for k. So assume that 10 to the k plus 1 plus 10 to the k plus 1 is divisible by 3. Well, what's another way of writing that? We could say 10 to the k plus 1 plus 10 to the k plus 1 is equal to some multiple of 3, so 3 times, say, L, for some integer L. So we need to use this fact at some point. So now we want to show that the next case, if I replace the n's in here with k plus 1, that that's also divisible by 3. So let's look at it. That would be, if I put a k plus 1 in for each of these n's, I get 10 to the k plus 2 plus 10 to the k plus 1 plus 1. Now I need to somehow get something like this inside of this. And the way to do that is in the first two, I'm going to factor out a 10. So I get 10 times 10 to the k plus 1 plus 10 to the k. Well, that's looking a little bit familiar, and then plus 1. So that is this part here. So if I move this 1 over, then I can use some substitution. So 10 to the k plus 1 plus 10 to the k is 3l minus 1. So that means I can replace this in parentheses here with 3l minus 1. So I have 10 times 3l minus 1 plus 1. Well, let's do some more work here. I can multiply the 10 through. So this is 30l minus 10 plus 1, so minus 9. And now we can see that this is divisible by 3 because I can factor out a 3. So this is 3 times 10l minus 3, whatever that happens to be. But that is a multiple of 3, just like we did here. It was 3 times 37. It's 3 times something. We don't really care what that something is, but it is a multiple of 3. So that does prove, using induction, that it's always divisible by 3. Next, we have that x is a non-negative real number, and we want to show that 1 plus x to the nth power is greater than or equal to 1 plus nx, as long as n is greater than or equal to 0. So here our induction will actually start at 0, which is okay. You can start at 0. You can even start at a negative integer, but you do need a starting point for induction. So let's look at our base case here. So when n is 0, I have 1 plus x to the 0. Is this greater than or equal to 1 plus 0 times x? Well, this is the same as 1 greater than or equal to 1, and that's certainly true. Okay, now let's look at our induction. So we assume that it's true for some k. So 1 plus x to the k is greater than or equal to 1 plus kx. So this is going to be a tool that we'll use at some point, because now we want to show that it's also true if the n was replaced by k plus 1. So we'd like to show that 1 plus x to the k plus 1 is at least as big as, so I'm going to put this way at the end here, 1 plus k plus 1 x. So I want to show this is greater than or equal to, so somewhere in here I need a greater than or equal to this. So in between I can have chains of greater than or equal to, or I could have a greater than, or I could have equal tos. Those are all fine, but I can't have a less than somewhere along the way. That would break the logic. Okay, well, starting here, I can certainly break this up into 1 plus x times 1 plus x to the k, just rules of exponents there. And I do that because now I know that 1 plus x to the k is at least as big as 1 plus kx. So I can say this is greater than or equal to this 1 plus x times just replacing this with this, 1 plus kx. So just to see what happened there, I just replaced that with that. And changed the sign from equal to greater than or equal to, since that's what the sign is. Okay, so we're trying to get to here with, again, either equal signs or greater than or equal to signs. Let's multiply this out. So I have 1 plus x plus kx plus kx squared. So that's just an equals to. Now I actually see that if I were to multiply this out, I'd have 1 plus kx plus x. That's these three terms here. So these are already equal. So the only extra thing is that. But since x is a non-negative real number, this is, actually it doesn't matter, this is always positive, right? So I have something plus some positive number, and then that's something on the other side. So that's going to be at least as big. And so that way we got it. We have that 1 plus x to the k plus 1 is at least as big, just following the chain, as 1 plus k plus 1 times x, which is what we wanted to show. Okay. Next, we review the idea of a power set. So we'll look at the power set of a set with 0, 1, 2, and 3 elements, and then we'll establish a pattern that the power set always has 2 to the n elements if the original set has n elements. So remember that the power set of a set is the set of all subsets of that set. Let's just put that up here. So the power set of a set A is equal to the set of, let's say, x, here's supposed to be a capital X, such that x is a subset of A. So let's look at the first few cases to make sure we understand what this is. So if it has 0 elements, then A is just the empty set. And so the power set of the empty set is all the subsets of the empty set, but there's only one subset of the empty set, and that's just the empty set. So it's just the set containing the empty set. Notice that this has one element in it. The empty set had 0 elements, but this, again, I mentioned this before, this is like a bag containing an empty bag. So inside the outside bag has something in it, namely an empty bag. So this thing has one element in it, namely the empty set. If n equals 1, then we'll just make a set containing one element. We'll just call it the set containing 1. So then the power set, all the subsets of the set containing just 1. Well, you have the empty set. The empty set is always a subset. And then you have the whole set itself. So you either have 1 or not. So this has 2 elements. So far the pattern's there. 2 to the 0 is 1, 2 to the 1 is 2. Let's look at two elements. So a two-element set, we could have 1 and 2 as our original set. So the power set of that, all the subsets of 1 and 2, well, you could have the empty set. You could have 1 by itself, or you could have 2 by itself. Or you could have the whole set 1, 2. So those are all the subsets of the set 1, 2. And again, notice this has 4 elements in it. Now for n equals 3, we are of course going to get 8 elements, but we want to actually start thinking recursively or inductively, however you want to think about it. So let's say we have a set with 3 elements. We'll just do 1, 2, and 3. In the power set, let's think of this as coming from the set before. So the set before had 1 and 2, so you have this sort of new element of 3. So all the subsets would be including all the subsets in the previous set. So it'll have the empty set, it'll have 1, 2, and 1, 2. But then we can get the rest of them by just saying, well, every other subset has a 3 in it, and if it has a 3 in it, it has something else or maybe nothing else. We can think of that as just adding or inserting the 3 into each of these. So if I insert a 3 into this one, I'll just have 3 by itself. If I insert it into that one, I get 1 and 3. If I insert it into this one, 2 and 3. And finally into this one, I get 1, 2, and 3. Giving us, again, a total of 8 elements, which is 2 to the 3rd. But viewing it in this way, we actually see that doubling effect, and it'll help us in the induction proof. So we've already shown a base case here, so we're just going to show, we've shown 4 base cases here. So we're just going to show the induction step. So assume that a power set of a set with k elements, so assume that it's true for n equals k, contains 2 to the k elements. So it's the power set that has 2 to the k elements. The original set has k. Maybe we'll give this set a name, the set A. So now we'll, again, think of it this way. So we'll insert a new element, say x, into A. So we'll say let A star be A union a new element x, where x is some new element. So x is not in A. Then, of course, A star has k plus 1 elements. We use the notation. So A star, the cardinality of it is k plus 1. So now we want to show the number of subsets is 2 to the k plus 1. Well, if we think about the subsets that it would have all the subsets that A would have, just, again, how we did that. So the subsets of A star include the 2 to the k from the power set of A, and by inserting x, we get 2 to the k more. And you can work backwards. You could say, and any subset of A star would either have x or not have x. So if it doesn't have x, it's one of these 2 to the k from A. And if it has x, then if you remove it, then what you are left with is one of those. Like if you remove 3 from each of these, you get back to one of these. So it has exactly 2 to the k plus 2 to the k. So the power set of A star, its cardinality, we know is 2 to the k plus 2 to the k. So the 2 to the k from A, and the 2 to the k you get from inserting an x into each of these 2 to the k subsets. But this is 2 to the k plus 1. Adding two powers of or alike powers of 2 gives you the next power of 2. And finally, for this video, we will show that that principle of well ordering implies the principle of mathematical induction. So they're actually equivalent to each other, so this is like 1/2 of that proof. So you would have to show the other way too, that the principle of mathematical induction also shows well ordering. But here we're just going to show one direction. So what would that mean that we're actually trying to show here? So if you have a set of natural numbers where 1 is in that set and n plus 1 is in that set whenever n is in that set, then S is the entire natural numbers, and we're going to get this from well ordering. So let's look at what a proof would look like here. So suppose S is a subset of natural numbers where all this happens, so such that it contains 1, and let's write it this way, whenever, or if n is in the set, that implies n plus 1. N plus 1 is in the set. So that's just what induction does. Now, to use the principle of well ordering, you end up using contradiction by looking at a set that's supposed to be empty and assuming that it's not. So we're going to consider, well, that's generally how you use the principle of well ordering. So consider x is going to be what you would get if you take all the natural numbers and subtract out s. So since we're trying to show that they're actually equal, this subtraction should be nothing. This should be the empty set. So x should be empty. But for the sake of contradiction, let's suppose x is non-empty. So suppose, for the sake of contradiction, x is non-empty. So we have a non-empty set of natural numbers, which we know a non-empty subset of the natural numbers is well ordered, so it has the smallest element. So that's the whole reason why we have this setup, so that we can give ourselves a non-empty set, and so we know it has the smallest element, or a non-empty set of natural numbers, then we know it has the smallest element. So our next statement is to say, by well ordering, x contains the smallest element. Let's call this little x 0. Well, if that's in x, then that means it's not in S. So this is an element that's not in S. But if that's the smallest element, then if I look one smaller than x0, then that must belong to S. So I want kind of a picture of what's going on here. This is all the natural numbers, so starting at 1. Then we know 1 is in S. And so what we're kind of saying here is that 1 has to, or that S has to stop at some point. So we're thinking S looks like this, and then X sort of takes over from here. And in fact, they could have some overlap, potentially, but the smallest element is x0. So that means if I go one smaller, it can't be an S because, or it can't be an X because that would be a smaller element than in X. So the next smaller element, x0 minus 1, must be an S. So this means x0 minus 1 is an S. But now we're assuming I think I have this backwards. So we're actually assuming the principle of mathematical induction is true. Or no, oh, yeah, no. We do start with this part of the principle. So the conclusion of the principle of induction is that this happens. So I don't have it backwards. We are assuming that well ordering is true, and that's where we just use that here by saying that it has a smallest element. But we can think of this as our n for this. So if n is an S, then the next element is an S. So if this is in there, then the next one is in there. So this implies that the next element is an S as well, but that's also saying that x0 itself is an S. But that's a contradiction because x0 is the smallest element in X, which is elements that are not in S. So here we get a contradiction. This is my symbol for contradiction. So that contradicts our assumption that X was not empty. So the conclusion we get from that contradiction is that X is empty. So X is the empty set. I'll put a little therefore. Therefore, X is the empty set. Well, if X is the empty set, X was the difference between the natural numbers and S, well, then they must be equal to each other. So our second conclusion here is that S is actually equal to all the natural numbers. Okay, we'll stop there.